Hello everyone, I am Shaurin Rahman and I'm gonna present our research on monitoring and predicting riverbank erosion in the Jamuna River Basin. In this study, harness the power of remote sensing and machine learning within Google Earth Engine to address the environmental challenge in Bangladesh. Riverbank erosion in this region devastates the communities, destroys the agricultural land, and threatens the infrastructure. Our goal is to predict erosion patterns and identify high risk zones to support disaster preparedness and sustainable land management. Here is our roadmap for today. We will start with an introduction, dive into the literature review, detail our methodology, present our results and discuss implications, and conclude with future prospects. Each step builds towards a comprehensive understanding of our approach and its impact. The Jamuna River Basin is one of the Bangladesh's most dynamic and erosion prone regions. Experiences severe riverbanks shifts that displace thousands of people annually. Our study introduces an innovative approach to monitor and predict these challenges using Sentinel-2 satellite imagery processed within Google Earth Engine. We leverage the spectral indices NDVI for vegetation health, MNDWI for water body detection, and EVI for enhanced vegetation analysis. Alongside the techniques like cloud masking, atmospheric correction, and temporal compositing. These tools allowed us extract riverbank positions, engineer predictive features, and classify risk zones using machine learning. The ultimate goal is to provide actionable insights for early warning system and policy planning, helping communities to mitigate the impact of erosion. Let's explore the research literature review. Our work builds on rich foundation of prior research. Studies like Billa and Vishwas mapped erosion patterns in the Jamuna River but stopped short of dynamic or predictive modeling. We drew inspiration from spectral indices like NDVI, MNDWI, and EVI, widely recognized for their effectiveness in vegetation and water body detection, as cited in the references. Cloud detection algorithms such as FMask and Sentinel-2 adaptations were critical for ensuring clean optical imagery by removing clouds and shadows. Additionally, machine learning techniques like random forest and convolution neural networks have revolutionized the water body extraction and change prediction. By combining these advancements, we develop a robust framework that beyond static mapping and predict future erosion risk. We use Sentinel-2 imagery from 2015 to 2023, carefully selecting images with less than 10% cloud cover to ensure data quality. The preprocessing phase were critical. We applied cloud masking using QA60 band to remove cloud inference, perform atmospheric correction with CEN2 core for accurate reflectance values, use temporal median compositing to create consistent datasets across seasons. We computed three key spectral indices NDVI to delineate the water bodies, EVI to enhance vegetation detection in dense areas. Adaptive thresholding on MNDWI enabled precise water body extraction, setting the stage for riverbank analysis. To extract riverbank positions, we use MNDVI WI thresholds to create water mask. which we converted into vector polygons and simplified with 10 meters tolerance. Annual changes were quantified, allowing us track erosion and deposition patterns, incorporating spectral indices NDVI, EVI, MNDWI, spatial data like coordinates and distance to the river, temporal lagged indices and interaction terms to capture complex dynamics. Our machine learning pipeline split data into training 2015 2021, validation 2022, and test 2023 sets. We tested models like linear regression, XGBoost, Light GBM, and CatBoost, optimizing them with grid search and evaluating the performance using R square and mean square or error. Finally, K-means clustering in k equal to 3 classified areas into high, moderate, and low risk zones based on the erosion rates and MNDWI variance, providing a clear risk map. Our analysis covered 8,928 data points, revealing key insights. Statistical summaries shows mean values of 0.082, uh, 0.282 for EVDI, 0.255 for NVDVI, and minus 0.071 for MNDVI from 2015 to 2023, with standard deviation reflecting seasonal variability. Temporal trends highlighted distinct patterns during monsoon seasons, June to September. Elevated in MNDWI correlated with erosion rates of 15-20 meters per year, while dry season, November to March, showed lower MNDWI, increased sediment deposition. The flood events in 2017 and 2020 caused sharp MNDWI spikes and peak erosion. Especially 30% of our study area was classified high risk, characterized by low NDVI, EVI, and loose sediments, particularly in the upper reaches. Moderate risk zones covering 45% showed transitional dynamics, while 20% were low risk, typically in concave river bends with high vegetation cover. Our machine learning models delivered outstanding performance. Linear regression achieves perfect R square of 1 and with an MSE of 1.0763 times, while 10 to the power minus 32. While XGBoost Light GTM Cat Boost score R square value of 0.9996 to 0.997, demonstrating an exceptional predictive and accuracy. This results profound implications by identifying high risk zones, 35% area. We can prioritize intervention like embankment, reinforcement, or reforestation. Our model was enabled to early warning system alerting communities to potential or erosion during the monsoon or floods. This study advances prior work by integrating predictive modeling with automated Google Earth Engine workflow. Unlike earlier studies that focused on static mapping, our approach leverages clean datasets thanks to the tools like fmonks and high accuracy models to forecast erosion dynamically. This scalability of our framework makes it adaptable to other rivers in systems, offering a blueprint for our global environmental monitoring efforts. In conclusion, our study successfully integrated remote sensing and machine learning to monitor and predict riverbank erosion of Jamuna River Basin. This workflow identified 35% high risk zone, 45% moderate risk, and 20% low risk zones, providing a global and robust framework for disaster preparedness, and scalability. This research empowers the policymakers and communities to act proactively, mitigating the impacts of erosion in vulnerable regions. Thank you everyone for your attention.